Good morning, good afternoon, good evening, depending where you are. So welcome to the summer workshop in mathematics, Universidade de Brasília. It's a great honor for me to introduce Professor Francesco Russo. He's a distinguished mathematician, distinguished professor of mathematics, ENSTA, Paris Tech, Institut Polytechnique de Paris. Along his career, Professor Russo has contributed to many different areas of probability theory and its applications. He's widely known for seminal and fundamental papers on stochastic differential equations with distributional drifts, probabilistic representation of partial differential equations with irregular coefficients, non-semi-martingale analysis. Together with Professor Pierre Valois, he has developed the so-called regularization, stochastic calculus via regularization, which proves to be a very powerful tool in the analysis of non-semi-martingale process, Gaussian process, with many applications, even in mathematical finance, in stochastic partial differential equations. So today, he's going to talk about Fokker-Planck equations with terminal condition and related McKean probabilistic representation. So thank you very much, Professor Russo, for your presence here.
Thank you very much, Professor Ohashi. It's really a great honor for me to take part in this important workshop in mathematics. It doesn't happen to me very often to be in a workshop about which represents all mathematics. And I would also like to thank all the organizers, in particular Professor Jacqueline Mesquita. So, in fact, the topic today, as Professor Ohashi said, concerns Fokker-Planck equations. And so Fokker-Planck equations are, in fact, second-order parabolic PDE, but whose solutions are essentially measures, and they are known when you fix an initial condition. So this talk covers joint work with my former student, my present student, Luca Isidorczyk, Nadia Ujan by Electricité de France, and Gianmario Tessitore from Bicocca, Milano. And the first paper concerns the topic of the talk. The second one is more a survey paper about McKean Feynman-Katz probabilistic representation. So since I am supposed to speak to a larger audience than usual, I decided to speak at the beginning about very basic things, which can be understood by everybody from analysis, let's say, and from PhD students. So the beginning will be very elementary. Later, I will speak about the spirit of the probabilistic representation in itself, of some PDEs or other deterministic problems. Then I will enter into the core of the subject, which means the Fokker-Planck equation with terminal condition. Because in general, those equations are more studied with initial condition. It's quite particular to have them with a terminal condition. And then we will speak about uniqueness and well-posedness, about those backward Fokker-Planck equations. And then we'll speak about their probabilistic representation. I will explain what does it mean, McKean type problem and so on. And at the end, I will mention something about some current work which concerns semilinear PDEs and control problems, but this is ongoing and it's not yet even a preprint. So let's come back to the basis, the complete basis. So stochastic differential equation and PDEs. So this is really something which covers a big part of stochastic analysis. And yes, Professor Ohashi spoke before about non-semi-martingales. In fact, what we will need here is even something more particular than semi-martingales, what we call Ito processes. So if you know what is a Brownian motion somehow, then Ito process is something like this. So you have a type of integral with respect to Brownian motion, which could be multidimensional, and then a classical Lebesgue integral. So this X will be enough for us for what we will do. So now what probabilists do very often is they apply some rules, some chain rules, they make some calculation, and at some point they take the expectation. And the good news is that very often when you take the expectation of a stochastic integral with respect to Brownian motion, or also with respect to other martingales, the expectation is 0, so it simplifies the calculations. So then a stochastic differential equation, it's really the analogous of an ordinary differential equation. For instance, if we have A equals 0, and in general is denoted like this. It's an integral equation, in fact, and the A is called the diffusion term and B is the drift term. Now, as you see, this can model a signal or a particle, and you have or a dynamical system, and the functions B and A depends on the time and the position of the particle. What a McKean stochastic differential equation is something relatively fashionable today, but it was introduced in a simplified case by McKean in '67. And in those equations have coefficients which do not only depend on the time and the position of the particle, but also on the law of the random variable xs. Of course, this dependence can happen in several ways. One possibility is to depend in a smooth way. If it depends, for instance, on a moment or on the variance of the random, then the dependence is relatively smooth. It's continuous with respect to what people call this Wasserstein distance and this kind of thing. But we will focus here more on a more singular dependence, where you have a dependence on the density. So if the law has no density, for instance, this does not make sense. Exactly. So this type of SDE, of McKean type, today one uses a more fashionable word, which is mean field. So it's related to mean field. Now, a tool, again, I'm sorry for the audience which comes from probability, but in fact, there is a formula which is called Ito formula, which is extremely popular in probability. And I'm sorry, here there is a typo. So this is a function of C2 defined on, just a moment, maybe. This is really a stupid typo. And this... so there is a moment in which... So here it's just a function of class C2 defined from RD to R, for instance. So then this is a generalization of fundamental theorem of calculus. And if you have a Ito process as before, the expansion gives you some first order term and some second order term. So for instance, if your process X were differentiable, this term wouldn't appear. And this is very, very popular in stochastic analysis. And what is the spirit of probabilistic representation in general? So in general, you have a PDE or a deterministic problem, and this is related to analysis somehow. And then you represent this by a probabilistic tool, which is very often a solution of a stochastic differential equation on any way a process, a stochastic process. And this has a double use. First of all, you have a modeling aspect, because the deterministic tool, the PDE, models some macroscopic phenomena, and the process gives you the microscopic point of view. And modeling phenomena, you have seen, you have listened about those things in many topics like biology, chemistry, complex systems, economics, and so on. And there is another aspect of this, is the numerical simulation. so that you would like to provide some Monte Carlo suitable methods. So by simulating the process and associated objects for approaching the solution of PDEs. So the macroscopic equation, typically, there are different types of macroscopic equation, but here we focus on Fokker-Planck type equation. And one very example, this is, I don't know if really you see immediately which kind of equation is, but let's think, for instance, a very simple case could be a porous media, for instance. No? If you have, I don't know, B equals 0 and sigma equals some function phi of u, and so on, then you get the porous media equation. Okay, something like this is a typical example. So I mean, there are many equations that can be represented, but in fact, sometimes one has to extend a little bit the framework of Fokker-Planck type equation. But this is in generally an equation, second order equation, whose solution are measures because you have conservativity here, and the initial condition is prescribed. The corresponding, I said porous media, it could be also the heat equation. A corresponding equation is the microscopic equation, which is an SDE. The SDE is given like this, okay? I write this in this way. So you see a solution of this equation is in fact a couple of a process and of a function. And the function is the low density, or sometimes it's associated to the low density, okay? So the most simple case, if you take sigma equal 1, B equals 0, we have Brownian motion, and the macroscopic equation is the heat equation. And now this U, this density, is in fact an idealization of the empirical measures of the particles, of a system of particles. Okay, now the meaning of probabilistic representation. What does it mean, probabilistic representation? There is a very simple concept. If YU is a couple solving the microscopic McKean equation, then U solves the macroscopic PDE. So this is the classical thing. And this is very elementary. You can do in your courses of first year of stochastic calculus. Fixing D equal 1, you take a function in C0 infinity. You apply Ito formula, as I said you before. Okay, you make appear, sorry, here there is another typo. Sorry, this, it's DS. Then you take the expectation, you kill the stochastic interval with respect to Brownian motion, and once you take the expectation, you get this, okay? Because you are taking into account the fact that U is the low. So you have low density. So you get this equal this plus this plus this. But this, it means exactly that U is a solution in the sense of distributions of the PDE, for the macroscopic PDE. So if you have, and this is very elementary, in this sense, you have a probabilistic representation. Of course, if you have a PDE, to find a solution, a microscopic process which represents it, it's a more difficult task. And in my survey paper, we give a lot of information about this. Okay, and now let's enter into the core of the subject. So the probabilistic representation of a Fokker-Planck with terminal condition. Because in general, I said, what is relatively well understood, but also there is a lot of research today, is to consider a Fokker-Planck with initial condition. It's what I was speaking about now. Now, as I said, an example of Fokker-Planck equation is the heat equation. Okay, dTu is equal to 1/2 Laplace of U. But in general, it's put with initial condition, not with terminal condition. Okay, now, so we have an equation of this type where mu is a prescribed probability measure at the end. So this is a typical problem which interests us, the core of the problem. Okay, now this type of equation, even in the in the deterministic literature, analysis literature, not very many people are aware about this type of things. There exists some literature. If you look at our paper, we put some literature in analysis about this, but it's not so well, it's not so used by many people. So what could be the motivation? We have in fact a first motivation which corresponds to inverse problems in physical science. So for instance, the determination of initial position of a diffusion phenomena. So in some sense, you observe the end and you want to recover the beginning, okay? And for this type of problem, we have sometimes lack of uniqueness and stability. For instance, those papers, Tikhonov and Arsenin and Lattès and Lyons, they discuss this kind of problems and some type of equation like this. Now, for this application, in some sense, we are more concerned by uniqueness than existence, because you will not have always existence for this equation. Even for the heat equation, if you prescribe the final condition, you don't have necessarily a solution. So, and a probabilistic representation for this kind of equation that we call BFPE, so backward Fokker-Planck equation, gives some new insights to the treatment of well-posedness and numerical approximation. And we did some application. We are doing, in fact, now with Nadia Ujjan, extension to semi-linear equation, particularly to represent a solution of Hamilton-Jacobi equation, Bellman equation, which intervene in control, for instance. So, in general, I come back to the PDE with initial condition. So this is much more understood, of course. And it is also quite well known, even though there are also some theoretical issues when the coefficients are very singular and so on. But essentially, it's associated with the solution of an SDE of that type that I said before. So then this one is associated to this in the sense that if you have the family of solution to this, you can obtain solution to this. But this is with initial condition. So if you want to, and for this we don't need any McKean, you don't have dependence on the law for this, on the forward one. It will be the case for the backward one. Okay, first of all, we speak about an associated analytical problem, which is the uniqueness for the backward Fokker-Planck equation. So this will intervene a lot. So we denote by MF of RD, respectively M plus D, the set of signed measures, respectively non-negative finite measure on RD, Borel sets of RD. So, of course, as you expect, we will think in the sense of distribution. If you have a mu, a finite measure, we say that U 0t with value in the finite measure solves the BFPE with terminal value mu if for every test function and for every t we have this. So the test functions are considered for simplicity only in space. So you see, this is the typically sense of distribution for our equation. And LT is the generator. Like this. So for this, in fact, one knows quite everything. But now let's come back to the final one. So I mean, for the initial condition. For the final condition, I would like to, it's not so obvious to treat this, okay? In the literature, there are not so many papers. But I would like to stimulate the discussion somehow by starting by an elementary equation. just the backward heat equation. You take a final condition, dtu is equal 1/2 Laplace, ut is mu, and the u is in the space of finite measure. We can take a larger space, of course, even S prime of Rd, but let's take this. So we want to show uniqueness. Uniqueness, it means there is at most one solution. And this is really very well known by analysts, but it's important to, the technique, I mean, it's important to emphasize this. If you take the Fourier transform of this, solves for every psi an ODE in S prime of Rd, okay? And this ODE has a terminal condition, but since it is an ODE, it doesn't care if it is forward or backward. So this ODE has a unique solution, at most one solution. Okay. So now another case which is relatively elementary, but more interesting and not known, it's what we call the Einstein-Willembeck case. So this, it's written like this. When you say Einstein-Willembeck case, essentially we have a PDE where the drift B is affine, which can be also time-dependent affine, CS of x, and sigma is continuous from 0t to the space, to the matrix. And this could be, in general, when you think in terms of forward representation, people, they know, probabilists, they know very well that this is solves this equation somehow. So it's sigma t dwt and then plus b t xt dt. And in general, the solution is a Gaussian process, but you can consider also non-Gaussian processes if the dynamics is the same one. So you can consider a terminal condition, not necessarily Gaussian. And at this level, we can also consider that sigma is degenerate. It's completely degenerate. The case is sigma equals 0. So then the PDE, the corresponding PDE backward Fokker-Planck equation with terminal value admits uniqueness in the sense that it admits at most one measure-valued solution. The measures can be also signed. And the idea of this is that given a solution of this backward FPE, you take again the Fourier transform, you have to do some manipulations, and here you have some terms which need to be defined at the distributional level. But anyway, in the first step, you suppose that the Fourier transform is C1, and then you give a sense to everything. And then, and C, it's the solution, it's this sort of exponential system, dt of ct. You know, this C is different from this one. This is script C. So a sort of exponential, so the solution of this backward matrix ODE. And then by making the change, if you take, given a solution U of this, f of u of this Fourier, and you put, you consider f of u of t calculated in CT, this solves again a well-posed backward ODE in S prime, which is this one. And so this determines V hence f of u. Okay, so this again, we have a simple case that can be treated at the level of uniqueness, quite simple. There are other cases which become now a little bit more complicated, but first I would like also to give some other simple things. So suppose that you restrict in the class, on some class, okay? And now, so the initial condition, you consider solutions with a prescribed final condition, but such that they start on some class D. And you suppose for the moment, the following hypothesis, that for every nu in D, the forward Fokker-Planck equation with initial value of nu has at most one solution. And you denote by u nu. Okay, you will say, okay, now you go back to the forward. But you have to understand that at the forward level, this is not a restriction. This is not really a big restriction, because you have a lot of examples where you have well-posedness for the forward equation, uniqueness for the forward equation of Fokker-Planck type. And if you take, for instance, a famous paper of Figalli, 2008, even for D equal P of RD, the probability measure on RD, this is equivalent to the uniqueness, for in this case, D equal P RD, you have equivalence to the uniqueness of solution in law of SDE, so the strong Varadan Martingale problem. So if you have uniqueness for the SDE in law, then you have uniqueness for the PDE with initial condition. Now, and there are many sufficient conditions for this. I don't want to enter on this, but the problem of well-posedness is very well understood, and in particular when sigma is non-degenerate, you have a lot of things. Now, if you consider, for instance, the case where D, the space of initial condition, are multiple of Dirac, and then we can focus two different assumptions. One with some possible regularity, in the sense that B sigma are Lipschitz with linear growth in space uniformly in time, but they could be degenerate. Okay, and another assumption where you can consider irregular coefficients, B and sigma bounded, sigma continuous, and non-degeneracy for the matrix sigma sigma star. In both cases, you can say something about uniqueness. And for instance, suppose that you are in the situation of the uniqueness for the forward Fokker-Planck with respect to D, then the following hold. If you take D equal M equal 1 and the more regular case, then you have uniqueness for the backward Fokker-Planck equation. In the case, for instance, at high-dimensional, it's more involved, and in the most general case, I don't think it's known, the answer. But, but anyway, we can show that there is an horizon which is sufficiently small such that the problem has uniqueness. So the sketch of the proof is that, for instance, suppose that the assumption holds, then if you are, in the case regular or irregular, this assumption, and you use Ito formula, and you can show that you, by the same technique, Ito formula, and you get that U alpha delta X is equal to alpha L XX, where XX is the unique, respectively unique, weak unique. Zvonkin gave a good condition in 74 about the existence and the weak uniqueness in law about this of the SDE, and you can conclude because first of all essentially we can use this and some injectivity property. So let's to illustrate this, suppose that you are in the case D equal M equal 1. The proof lies essentially on the fact that expectation of xt is equal to expectation of xyt. So you have two solutions, one starting from x, the other one starting from y. Then you write z xy as the difference of the two. Then they solve this problem where bs xy is equal to integral 0 to 1 dxb s a xy s plus 1 minus a xx s dA. The same for the diffusion coefficients. And then you get that, so this, since the coefficients are Lipschitz, these are bounded spatial derivative in the sense of distribution, and you arrive to this expectation of the exponential of the integral 0 to t of b x y s ds, and times the Doléan exponential of this process, integral 0 to t sigma xy s dws, times y minus x. You have made written an expansion at the first order, but this is always positive. So this implies that y equal x. And so in particular, delta y equal delta x. And so you have, if you have identified the initial condition, then you have uniqueness, because you have uniqueness for the problem with initial condition. Something similar happens in the irregular case, but unfortunately, this is true only for small capital T. So in the paper of Zvonkin, one can show that there exists phi such that phi defined on 0t cross Rd with value in Rd, such that phi 0 dot is injective, but he has to take T small, and you remove the drift so that this phi dot xx and phi dot xy are martingales, and so you get that phi 0x is equal to this because we have a martingale now. Phi of the process is a martingale, and this is equal to this because of the final condition, which is the same. And then this is equal again by the martingale property to phi 0 of y, but phi is injective, so this determines x, the initial condition. So this is just to show the type of techniques which appear in this simple case. A more involved case is the following one, and it's also much more general, not general, but more satisfying and complete at the level of result, because we don't need to restrict the space of initial condition. Until now, we restricted to the space of the initial condition of multiple of Dirac measures. Now, suppose the following. We have, for every I and j integers, bi and sigma ij are homogeneous, time homogeneous, bounded, and belonging to C2 alpha, all the space, for alpha between 0 and 1/2. Sorry, I don't think sigma is equal to sigma transposed. So I say that the limitation here is a time homogeneity, but we'll say later what we can say if you remove this. And also the non-degeneracy, so that for every x and y, sigma x, y is larger than epsilon y squared. Okay, in this case, we have a fairly complete result of uniqueness. But for this, we start with a lemma which is inspired by Lunardi, the book of Alessandra Lunardi of 95. So the differential operator L, which is the generator of the SDE, extends as a densely defined operator from C2 alpha plus 2 Rd to C2 alpha, generating an analytic semigroup, PT. What we use only is that for every initial condition, finite measure, the map which goes from T to integral of the Rd of PT phi x mu dx is analytic. And for this, so this is the key. And for this, we have that, suppose under this assumption, for every initial condition, for every final condition, the equation BFPE, the backward Fokker-Planck equation, with terminal value mu, admits at most one solution. At most one solution. So this is a complete result without restricting the space of initial condition. And the idea of the proof is the following. So you start with two solutions, U1 and U2, two solutions of this backward Fokker-Planck equation on 0t with common terminal value mu. Then you observe that through the mild technique, mild solution technique, if you have an initial condition nu, for t in 0t, the measure valued v nu, defined like this, as the integral of pt phi x nu dx, nu is the initial condition. This solves the Fokker-Planck equation forward from 0 to t with initial value nu. So this, we know that this is a solution of this. This is the second observation. And then there is again this discussion about the uniqueness of Fokker-Planck equation with initial condition, which happen quite often. And this we use in a very important manner here, and in the following way. Suppose that we have T0 and T1, 2 time, nu in MF of Rd, and we consider the equation FPE, the forward Fokker-Planck equation, with initial time T0 and terminal time T1. In our case, it will be T0 equal T and T1 equal to T, for instance. And initial value nu, this admits a unique measure value solution by these techniques of Figalli. So this, you know this, you have uniqueness for the forward. Now, we consider, we start with our solution. U1 and U2 are our 2 solutions. You fix with terminal condition capital T, which are equal. Now, you fix nu I, you define nu I as ui of 0. And then by previous points, we have that between 0 and t, this integral phi x ui t dx is equal to pt phi nu I dx. This is by uniqueness in 0, and the fact that the function v nu of before is a solution. So it has to be the solution U1. And starting from mu, you can continue to the future. Then you have equality, because if you consider a Fokker-Planck equation starting on capital T and you continue, then since mu is equal for the 2, then you will have equality. So then after capital T, you have equality of pt phi nu 1 dx equal pt phi x nu dx. But now, this is analytical, pt is analytical, so for every phi in C2 alpha, the difference of these 2 are 0 starting from T, from capital T. But by analyticity, there will be 0 on the whole domain. So in the whole open set, 0 to T, at least here. Because they are 0 from capital T to T. This is a typical property of analyticity, which determines the function. Okay, and so then we, setting T to 0, going to 0, we get nu1 equal nu2, and this ends the proof of the Fokker-Planck uniqueness. This ends the proof by the uniqueness of the forward Fokker-Planck. So this, in this context, we have a uniqueness theorem fairly satisfying. And this can be extended to the case of time homogeneous coefficients, but not completely. So we have a piecewise, we have a grid, and on this grid, we have the same properties as before. Okay, Hölder continuity, non-degeneracy, and so on. And for this, we extend the result. Since we were motivated by some numerical ideas, then we wanted to emphasize that even though we put homogeneity, we can extend to non-homogeneous case by taking some time independence on each interval of the grid. So for this, you have the same results of uniqueness. And now let's come back. Let's go finally to well-posedness of the associated equation. So we said that we want to represent probabilistically our PDE with terminal condition. We said we need a McKean type problem. McKean in the sense that even if your coefficient do not depend on the density, our problem will be will involve some drift term which depends on the low density of the solution, as we said before for the classical McKean problems. So the problem, we consider such a problem, and so B tilde is defined in terms of B in this way. So suppose that you are in D equal 1, you have the sigma square T minus T y multiplied by P, and then divided, you have the derivative of this, and you divide by P. So it's a sort of logarithmic derivative. minus b capital T minus T y. And so this is we interpret this as a coefficient which depends on the law. And so the solution is a couple psi and p. So we have really a McKean problem because we have psi and p. And pt is the density of p. So this denotes the measure object, and this the density, its density. So this is inspired probabilists. The probabilist people have recognized that this is inspired by the techniques of time reversal of diffusion, started by Hausmann and Pardue in '86. But I will show you now the difference. So formally, if X is a diffusion process with coefficient B sigma and sufficient regular marginal density Qt, then you have, if Q is the density, then this is the term which appear. So the X head, so the time reversal, solves the type of equation that we have. But a priori, Q is given. So the essential idea for existence is that it's provided by this Hausmann-Pardue representation. The uniqueness is more challenging, okay? Because if you don't know a priori that is the law of the process, then you have a real McKean mean field type problem. Now, let's discuss how we discuss also existence. We have to say something. We need some remark. First, we have to link, as we did at the beginning, the McKean SDE to the backward PDE. So the SDE should be linked to the PDE. This is a backward PDE. So backward PDE, sorry, PDE this is backward PDE in the sense that it's a PDE with terminal condition. It's maybe better to say explicitly that this is a PDE with terminal condition. That we discussed the uniqueness before. Okay, now, first of all, we have to clarify what does it mean to represent. So suppose that B and sigma are locally bounded. If mu is a probability, and then if psi p is a solution of the McKean equation, the couple, such that L of xi0 is mu, which is the terminal condition, then pt minus dot is a solution of the backward Fokker-Planck equation. So this one. So this is elementary, but one has to observe this. And this is an application of Ito formula, as you have seen at the beginning for the classical McKean problems. You apply Ito formula, you take the expectation, and that's it. This is, again, a good exercise for students. Now, concerning the well-posedness, we should discuss the uniqueness and somehow the existence. So we take the following assumption: B sigma time homogeneous, bounded, and Lipschitz continuous, non-degeneracy, and some property of Hölder continuity for the derivative of B of sigma and the second derivative, the Hessian matrix of sigma. Okay, under this, first of all, you observe that this implies the assumption A, under which we had uniqueness by these techniques of analyticity. Now, for all new FP, the Fokker-Planck equation initial value nu admits a unique PRD value solution U nu. So this is the forward representation by Figalli 2008. And we know that the backward Fokker-Planck equation, the analytical object, the PDE with terminal condition, admits at most one solution. Now, the theorem is that given a mu P of RD, which is the terminal value of a solution of the FPE, then MK, the McKean equation with initial law mu, admits existence and uniqueness in law. So the steps of the proof. So first of all, we need a preliminary lemma which says that every solution of our McKean equation under our assumption is such that the drift B tilde is locally bounded on 0t cross RD. Okay, so this is every solution as the drift as locally bounded. For this, okay, essentially you have mu in P of Rd such that mu is equal nu of t. Cp is a solution of McKean with initial law mu by the proposition of the representation pt minus dot solves the backward Fokker-Planck equation with terminal value this, and the uniqueness for this backward Fokker-Planck equation says that u nu is equal pt minus dot. So we suppose a priori that our measure, which is prescribed, it's in the target of our PDE, which starts at nu. Now, combining results given by Aronson and Friedman, that analysis people and most of probability people also know, we can show that on every compact of 0t cross Rd, we have a lower bound and upper bound for the P, the density of the semigroup, and for the gradient of P, you have an upper bound. And this implies that our drift B tilde is locally bounded. So every solution is such that the drift is locally bounded. For the existence in law, given nu such that mu is equal nu of t, and x is a strong solution of the forward SDE with initial law nu. So by Ito formula, this solves the law t sent to the law of xt solves the forward Planck equation with initial value nu. The uniqueness for the Fokker-Planck equation says that u nu is equal to the law of xt. Sorry, and now this implies that xt admits a density because by the last proof. And now we use the time reversal process given by Hausmann-Perdue to show that we have a solution to our problem. This and the proof is completed since mu is equal to nu of t, law of xt. Concerning the uniqueness, as I said, it's a little bit more involved. We have given mu p of Rd. This is the initial value, the initial measure of our backward McKean. So equation McKean with initial value mu admits uniqueness in law, admits between the solution Cp such that B tilde dot P is locally bounded. So if we show that we have uniqueness of our, so we have a given solution. If you show that automatically P is locally bounded, it's enough because we have shown that every solution is such that P is locally bounded. So let Cp such a solution. By the representation proposition, Pt minus dot is a solution of the backward Fokker-Planck equation with terminal value mu, but for this there is uniqueness. So therefore, the process Y now solves a classical SDE in the sense, a non-McKean, a classical SDE where you don't have anymore because you have identified the P. And so we have a classical drift, and for which those drifts are locally bounded. So you have a classical SDE, you can use the technique of classical SDE, okay, like Struck, Varadan, or Krylov, and so on. And since you have identified P, you identify also the process because of uniqueness in law once you freeze the P. And this gives you uniqueness. Pay attention that we construct a solution starting, provided our mu, initial condition of the backward problem, lies in the target of the Fokker-Planck equation. If we start outside the target, there is no possible solution. So it's not because we are not able to do this. Now, other important thing, if we work on the Ornstein-Willembeck dynamics, we get again a similar result, okay, of existence and uniqueness. And more generally, if you are satisfied about solution of the backward solutions of our McKean, which land at the final point in some class D, then the well-posedness for the backward Fokker-Planck equation, which is the analytical object, may correspond uniqueness for the McKean equation. Now, just some words about the, the current work. So we wanted to, to discuss something at the level of semilinear PDE. So now what happened is the following. We consider, for instance, Hamilton-Jacobi equation with some bounded non-degenerate matrix valued function T. Sigma is deterministic, which integrates the Brownian motion. And so the control is only on the drift. So the classical techniques of representation of those semilinear equations are given by backward stochastic differential equation by Pardue-Peng. I am at the end of the talk. Not everybody knows this, but people from probability know very well. So you need a forward, and then which is given by sigma t, ct, dwt plus some b tilde, but b tilde is arbitrary somehow. It's a drift that you have to subtract here. So you have a sort of degree of freedom. But anyway, you can represent your solution by a forward equation and a backward one. And in this case, if u, for instance, if C01, it's a sort of Feynman-Katz, okay? And of course, what we wanted, and we have implemented this, especially my colleague Nadia Ujan has implemented this. So the idea was to have a fully backward representation in the sense that the BSDE is backward, okay? Because it's an SDE where we prescribe the final condition. Now, the forward here is well settled for a fixed initial condition. But now we decided to have both backward in a different way. So we write the time reversal of this formally, and this gives us this equation, okay? But since we are we choose b tilde here to be affine, time dependent but affine in X, and sigma depending only on S, then here the dynamics is Gaussian. And so it's easier to represent the time reversal, okay? Which gives this depends from Q, which is the variance matrix, and from MC, which is the mean. And at the end, this is our forward, okay? Our forward, you start from a final value here, and you solve the problem. At the same time, you have to think about the backward SDE. So the other representation is also backward. So what was done in the classical case? In the classical case, one chose b tilde. For instance, Gobet and all these people, they chose b tilde in somehow arbitrary way, and then their problem was to simulate the forward process and then to stock also informations, and then in the way back you had to calculate regressions and conditional expectations. So the idea here is to do everything backward, okay? Everything backward. And one reason was that if you start with a general b tilde, the forward process is not visiting the important regions. And we wanted to visit the process, the important regions, in the sense that we are close to the optimal control process. The idea was this, to choose b tilde in order to be close to the optimal control process. So at the end, we have to choose a final condition, and this is a bit arbitrary, it's empirical, but it has to be somehow related to the support of G. And then we need a variance related to the final condition, which has to allow, because you can always solve this equation until the end, until zero, but those objects can be degenerate at some point, so non-invertible. So I mean, at some point, you have a problem. So you have to be sure that this solution can be solved on 0t. And for this, you need to choose the variance. And these are open problems for us that we treated a bit empirical. So the conclusion is that in this way, it's a first step to consider our technique of time reversal to have a representation which is fully backward, because psi is the solution of 8, and the x, the time reversal of this, is the classical forward process. And the values process, yt, it's supposed to solve the BSDE, and this is calculated also backwardly. So the psi is backward, and the y, so the conditional expectation, are also backward. We start with a Gaussian distribution, and we discover step by step B tilde, readapting it in a class of affine drift. So we keep the process Gaussian, but we try to keep it as close as possible empirically to the optimal control process. And there are some encouraging simulation results, but we are not, the mathematics, I mean, there are some mathematical aspects, but there is a lot of heuristic there that cannot be translated into mathematics for the moment. So this is a list of reference that I quoted during the talk. So thank you very much for your attention. I was, again, very, very proud to be with you in Brasilia, even if it's virtual. Thank you very much.
So thank you very much, Professor Russo. So now we have some questions here on the chat. Okay, so the first question is from Professor Christian Oliveira. The question is the following. So he asked about the reason for t is small in the irregular case.
I understand. So this, I have to tell to Christian that I think that this concerns only a very particular result. This in all of the results, t is anyway. Thank you, Carol. So in fact, the problem lies only on the technique, you know, because in the one-dimensional case you can solve explicitly. In the multidimensional case, thank you, Jacqueline. In the multidimensional case, if you see the technique of Dworkin that you know very well, they solve the problem of existence uniqueness in law by step. So for them it's enough to get this t small, and then they can solve the problem. But for us, we couldn't do better for this particular case. So because we needed something which is really injective. But Christian, again, this was a particular case concerning irregular equation and so on. So at the end, you know, the results are completely true for what we said about at the end about the techniques of analyticity and so on. These are true for every t. But so it lies on the technique. I think it can be solved. Thank you very much.
So,
thank you, Yuri.
Any more questions here?
Thank you, Felipe.
So I have a question. So it's just a curiosity for me.
Please.
So it's clear that they solved the McKean SDE to assess the backward Fokker-Planck equation. So is it possible to solve the PDE, the Fokker-Planck, and prove the McKean SDE, or not?
So you know in fact, for what I presented, in order to so our problem is really for the backward PDE. Our problem is really the uniqueness. You know, for the existence, you have no problem, because if you lie on if you start.
Yes, but I mean uniqueness. I'm sorry, not solving, but in terms of uniqueness. To assess
you mean the uniqueness of the SDE?
Yes.
Without using the PDE, you mean? Or
no, by using the PDE.
But we use the PDE in some sense, because we first use the uniqueness of the PDE, and then we inject on the equation, and then we have a classical SDE of Struck-Varadan, and for this you have uniqueness or in existence. So I mean we use both of them. Yeah.
Okay.
Yes, maybe you are wondering about some fixed point technique or to work directly on the equation, but our technique is really to use the PDE. Because of this, we do this part at the beginning.
And the fully backward representation is motivated by control. Is it correct?
Yes, exactly. Yes. So we really choose the forward. You know, in principle, if in the literature on BSDE allows you to choose any drift you want, because you can subtract from the driver, and you need a criterion to choose this drift. And this is what people do, as far as I know. Until now, they don't have really a criterion to choose this. And
with your technique, do you believe that it's possible to improve this choice?
I think that there is some mathematics to do there in order to find a good criterion to choose theoretical B tilde. What we do is that we do a simulation, a backward simulation, and by regressions, at each time we find the optimal drift in some sense, which is close to the optimal control process, which is a technique which could maybe be mathematized better, but for the moment is empirical. Mm.
Yeah. Okay. So any more questions? Okay, it seems not. Sorry, there is a question here.
Yes, I see the question. Yes, you know, in fact, you are concerning the first part. In principle, we have uniqueness and existence if and only if the terminal condition lies in the target. If you are referring to the second part of the talk, then there we have, this is what you say, it's really a big problem. Because when we start, the second part of the talk, we start with a law, and at some point you reach a singularity. Yes, you can solve your equation until some point. And then this is a problem, a theoretical problem, to know how to choose the initial condition, which is in fact the terminal condition, in order to be able to reach the beginning. And for this, it's for us, it's a bit empirical for this part of the talk. But concerning the problem of existence and uniqueness, then we have a theorem which says if and only if we don't have a final condition which depends on some mu at the beginning, then we don't have solutions. So it's a if and only if.
Okay. So I would like to thank
you, Jean,
very much, Professor Russo, for your very nice talk. It was a great pleasure your presence here, as I said before. So thank you very much, and thank you all the participants of this last plenary talk of the workshop in mathematics, Universidade de Brasília. Thank you very much. Bye bye.
Bye bye. Thank you.